Hi guys, meet the LiGrip O2 LiDAR Scanner. I shared my first review last week and it proved to be the best SLAM LiDAR scanner I have tested so far for scan-to-CAD building modeling. Because this device comes at a high price, one test video alone can't verify whether it truly meets professional standards. Today, I'll be testing the LiGrip O2 by scanning a 10,000 square meter parking lot spanning 5 levels in one continuous run. This has been my go-to benchmark site for SLAM LiDAR scanner for years, and up until June 2026, none have successfully passed this challenge. With its 80-meter driveway, this parking building has proven impossible for any SLAM LiDAR scanner to keep the floors level from one level to the next. In this test, I'm including the Manifold Tech Pocket 2 and the SHARE S20 as well, so we will see if any of the three scanners can succeed. The benchmark here is floor-to-floor leveling across an 80-meter driveway. Even with construction tolerances, deviation should not exceed 3 cm. Yet most LiDAR scanners I have tested drift by over 20 cm, far too inaccurate for reverse engineering. The next step is evaluating column alignment across floors. Next, I will focus on the column grids, orthogonality, and parallelism. The final evaluation focuses on column span consistency. Together, these 4 evaluations form the primary inspection criteria for LiDAR scan data in multi-floor buildings. If any of them fail, the dataset is unreliable and unsuitable for architectural, engineering, or construction use. Before we begin, I want to highlight the sensor differences. The LiGrip O2 runs on the Hesai XT32M, whereas the Pocket 2 and the SHARE S20 are built around Livox Mid 360 sensors. Looking at US retail sensor price, the XT32M is roughly 3 times the XT16 and 13 times the Livox 360. This figure reflects sensor pricing, not the complete scanner, but they are solid reference for the scanner's overall cost. Now onto the vertical field of view. The XT16 and XT32 share 30 degrees FOV, but the XT32M extends it to 40 degrees. This narrow beam design helped reduce noise and deliver sharper corner details, which my testing clearly shows. However, the sensor must orbit to capture the entire area without blind spot. Although marketed as a 300-meter sensor, the XT32M actually delivers the same effective maximum range as the XT16 and XT32, around 80 meters at 10% reflectivity. This is still about twice the detection range of the Livox 360. Scanning speed is the next factor. It dictates walking pace during a scan, with the XT32 and 32M running roughly 3 times faster than the Livox 360. Scans can be completed quicker, minimizing IMU drift that grows with longer scanning times. At a 10-meter detection range, manufacturer data shows the Hesai XT series achieving superior hardware-level precision. In contrast, scanners built on the Livox 360 need extensive filtering to approximate thin point cloud walls. with the XT32M costing nearly double the XT32. The key advantage lies in the precision range. It maintains under 10mm accuracy from 0.5 meter up to 70 meter, whereas the XT16 and XT32 don't perform well at close range. This could explain why the LiGrip O2 performs so well in the 3-floor house test. The corridors and rooms are relatively small, which plays to its strength. The Hesai XT series consumes about 40% more power than the Livox 360. And finally, the weight. The XT32M is about 40% lighter than the XT32, and the Livox 360 is about 40% lighter than the XT32M. The LiDAR sensor covers are made from polycarbonate, not glass, so they scratch easily. If dust collects on the cover, use a blower or wipe gently with a damp microfiber cloth and a glasses cleaner. Avoid wiping with a dry cloth or using solvents. These sensors are expensive, so it's important to know how to take care of them. Now let's begin the 3D scanning. I'll start on the middle floor, walk down 2 levels, return to the middle floor, then walk up 3 levels, and loop back to the middle floor. The LiGrip O2 doesn't include a first-person preview screen, which makes multi-floor scanning difficult. The point cloud from the upper floors often blocks the view, making it hard to interpret the scan as you move between levels. But it does have an elevation crop feature that lets you adjust the upper and lower limits of the viewport. Still, it's harder to use than a true FPV preview mode. This end of the wall measures 80 meters to the opposite side, and the underfloor height is only 2.2 meters. When I hold the LiDAR scanner, its position less than 1 meter from the underfloor. This can be difficult for the XT16 or XT32 sensor variants, since their effective range needs to be shorter than 3 meters. This floor has a taller underfloor height, so the floor-to-floor spacing can affect scan quality when using different LiDAR sensors. Here I'm reaching the top floor and returning to the starting point. The total travel distance is 847 meters with a scanning time of 16 minutes. When crossing the loop with a SLAM LiDAR, a good practice is to overlap the trajectory. Simply walk past the starting point in the same direction as when you began, like this. Next, I will scan with the Pocket 2. You will notice it has an excellent preview screen that looks very realistic. This example is from the older version of the mobile app. The newer version performs even better. And finally, the SHARE S20. Its preview screen is decent, but a low light warning pops up and takes over about 30% of the display. I reported this issue to SHARE, but it hasn't been fixed. With the screen already being small, the warning message ends up blocking most of the view. Let's take a look at the scanning result from the SHARE S20 first. I processed this dataset using the older software version 2.2.4, but it threw an error message. The error reported abnormal mapping, but the software was still able to output a non-colorized version of the point cloud. When I inspect the 5th floor, I found the surface was unlevel, leaning upward by about 20 to 30 centimeters, similar to the scan I recorded with the C1 a few months ago. Now I'm remapping the S20 data again, this time using the latest 2.5 final release version. And here's the result from version 2.5. The scan completely failed. If you plan to use the SHARE scanner for multi-floor areas, I recommend breaking the scan into smaller sections, each under 3000 square meters, and then align them together. For remapping, stick with the older 2.2.4 release since the new version is highly unstable. For the Pocket 2, I uploaded the scan data to the MyCloud X AI platform and processed the remapping online. And here is the result from the Pocket 2. I will show you how to identify the fail points in the scan data. Notice that the columns from the floor above and below are misaligned. This isn't a construction error, it's simply not possible. Next, look at the floor slab. The top floor appears thickest, the middle floor is thinner, and the lower floor shows only as aligned. This happens because the top and under floor lines lean towards each other. That alone is enough to declare this a failed scan. Just like with the SHARE S20, scanning a 10,000 square meter multi-floor building in a single pass is beyond the capability of the Livox 360 based scanner. You will need to break the project into smaller scans under 3000 square meter and then align them together. Now let's look at the LiGrip O2 result. The remapping took 74 minutes to process and the camera file reached nearly 28 GB for just a 16-minute scan. That consumes a significant amount of storage. The report claims that 100% of the scan data falls within 0 to 1 centimeter of accuracy. However, I know these accuracy reports aren't reliable. The scan produced 340 million points, and when checking the column alignment, they appear to be vertically aligned. This is how you first check scan data. Secondly, examine the floor slab thickness. The lines should remain parallel and maintain a consistent thickness. Building a suspended floor with uneven thickness is particularly impossible, so any variation here indicates a scan error. To truly verify the floor level, you need to check it in CAD software. Here is in BricsCAD. I will start by aligning the scan data to the X, Y, and Z axis. Then I will use the offset command to create reference lines from the first, second, and the third floors. From here, the floor is very level. When I extend the floor line across the entire length, the lines remain level and parallel to one another. The LiGrip O2 successfully passed the 80-meter floor leveling test. For the next evaluations, item 2, 3, and 4, I will model the entire parking structure. If there are errors, they will become evident during the reverse engineering process. I'll begin by creating the floor lines on this side of the building. When I offset the line from the floor above down to the floor below, they match perfectly. The same result appears when I offset the floor line upward to the floor above. The scan precision is excellent. I can even detect that the floor slab in the ramp area is about 75 mm thicker. Looking down from the top to identify the column grid lines, you will notice the wall lines of the columns remain thin even when viewed across multiple floors. That's a clear indication of good column alignment. From the top view, offsetting the column grid line shows the span at exactly 8 meters, confirming precise spacing. You can see a short wall at the center of the floor slab. In reality, that wall is a beam linking two levels of the slab together. With a depth of 30 cm, this cross-section exposes the hidden structure of the building, something engineers won't be able to detect with the conventional measurement methods. Now I'm going to array the columns at 8 meters spacing. All the columns align perfectly with the point cloud, confirming the scan data is highly accurate. Here's the best part. I will copy the elevator core and move it 48 meters along the y-axis. You can see the wall lines match perfectly with less than 10 mm of error. Here's the scan data of the underfloor pipe run. The pipes are clearly visible and easy to trace. By cropping the pipe cross-section, the diameter becomes identifiable because the point cloud is dense enough to capture the detail. The LiGrip O2 has officially become the first SLAM LiDAR scanner to pass this test. All SLAM LiDAR scanners on the market advertise similar claims of precision and accuracy, but each is built differently, both in hardware and software. That's why intensive testing like this is essential to confirm whether a measuring tool is truly suitable for architectural, engineering, and construction applications. In this test, the LiGrip O2 stands out as the top performer. This is not a paid review or sponsored video. The scanner was provided on loan and will soon be returned to the manufacturer. Thanks you guys for watching. I'll see you in the next video.